Good morning, everyone. So thank you for the invitation and giving me the chance to kick off this morning by telling you a little bit about planet formation, particularly the accretion, evolution, and loss of hydrogen helium atmospheres. Before I start, actually, I would like to acknowledge some of the people I had the privilege to work with. One is Sivan Ginsburg, who's right here. Then the other one is Akash Gupta, who's currently my grad student at UCLA. John Bierstecker, who's one of my grad students still at MIT. And then Almog Jalinovic, who is currently a postdoc at CETA. Okay. So I got interested in this problem. I've cared about planet formation all my life, as far as I remember. But I got particularly interested in sort of trying to understand from a planet formation point of view the accretion of gas and what happens to it afterwards. When these beautiful observations came out from the Kepler spacecraft that showed us that basically we have an abundance of planets that live in this period space of a few hundred days, or periods less than 100 days, and have radii somewhere between Earth and Neptune. And what's so intriguing to me from a planet formation point of view that we didn't really have analogs of these in our solar system, right? So we have Mercury, Venus, and Earth here, but we have 0 planets in our solar system in this region. And so it's sort of intriguing. This is the radius of Neptune drawn as a red line. So it's intriguing what on Earth is going on here. So we know, right, these planets to date are the most common planets we've discovered. So they're really abundant. Almost every other star in our galaxy has one of those guys around them. And we also know that a large fraction of them have radii that are so large, given their mass, that they must have some hydrogen-helium envelope. So that got me thinking of, well, how did you form these guys? You know, should we think of their formation sort of as a scaled-up version of super-Earths? Or did they form more analogous to Uranus and Neptune and then maybe migrated inwards? Or is it something completely different yet entirely? And so today I would like to give you sort of a brief overview of what we understood, I think, by treating sort of self-consistently the gas accretion, retention, and loss for this population. So I'm not going to worry about forming my core. So I'm going to cut out that part because I only got 45 minutes instead of 4 days. So let's just worry about the gas accretion part. So let's just think about it together. So if you have, let's say you give me a planetary core, and you ask me, well, how much of an atmosphere can this core accrete? Then the first thing that will be important is to know how large my core is. Because when you have a core whose physical size is smaller than its Bondi radius, so right, the Bondi radius we heard yesterday is sort of the distance where sort of the thermal energy from a gas particle, the velocity you get from that is equal to the escape velocity. So if you can only have an atmosphere if your Bondi radius is outside your physical radius, right? Because if the Bondi radius is smaller than your physical radius, even on the surface of your planet, your gas particle would not be gravitationally bound to you. So then that means you can only hold on to an atmosphere if you're bigger than a certain size. And now exactly how big, it depends, of course, where you are from the star and how warm your disk is. But just sort of a back of the envelope number to remember is you have to be roughly bigger than Ceres, our biggest asteroid. So a few hundred kilometers. So if you accrete the cores and you don't have a gas disk, you know, the accretion releases, you have to get rid of loads of gravitational energy, and that's done as heat, and that's very easy to radiate away if there's no gas disk. You can do that at sigma t to the 4th. Takes like days, it's super easy. However, if you start forming your cores in a gas disk, what happens, initially you're so small, your Bondi radius is smaller than yourself, so any heat that needs to be released to bind your core will be easily carried away by the gas, because it's not bound to you. But once you start to form cores that are so big that now your Bondi radius starts to be larger than your physical radius, some of the gas starts to be gravitationally bound to you, and now the heat cannot be carried away that you need to release from accretion by growing your core in the same way anymore. And in fact, what happens is you start accreting the envelope, your core will cool to just the temperature that is needed or that allows the gas envelope to be gravitationally bound to you. So you can sort of understand this. If it's harder than that, you would blow away your envelope, and then you would cool until you can extract that gas again, and then you would sort of be stuck again at this temperature at which hydrogen helium would just be able to be gravitationally bound to yourself. And you can calculate this at the back of the envelope, and this is roughly, right, it's just basically just depends on the gravity and the mean molecular weight of your atmosphere, and then depends on what planet you want. But for an Earth, between Earth and Neptune, it's between 10 to the 4 and 10 to the 5 Kelvin. The temperature of the core, and then you have this hydrogen helium envelope on top. So that's my little initial condition. Okay, but if you do this, and then ask, well, how much envelope do you have in this, in my Bondi radius, say, what you find, now you can pick your location in the disk, that this amounts to, at best, of roughly 0.01 to 0.1% of your total mass. So this is okay if you want a little bit of hydrogen helium. It's not sufficient, right? If you want to explain sub-Neptunes that have of the order of 1 to 10% in hydrogen helium, because we know they have to have created enough gas so they can roughly double their size, right? The hydrogen helium is able to have a significant effect on the overall radius we observe. So how do you accrete more than that? And we heard actually yesterday already from Sivan how to do this. What you have to do is you have to basically wait a Kelvin-Helmholtz timescale for the gas that's in your Bondi radius to cool and contract, so you can resupply material from the outside. So what happens in terms of the structure of your envelope, you have a large convective region, and you sort of start to develop a small radiative outer layer where you can sort of start to lose some of the material, some of the heat, so your envelope can contract and you resupply this material. So because of that, the cute result is that how much of an atmosphere you accrete does not depend to first order on the gas surface density in the disk. It's really driven mostly by the time scale you have for cooling, so that's why you have the disk lifetime in here. And of course, the opacity, because it is the bottleneck at the radiative convective boundary, because it tells you how quick you can get out, right? It's really important. So with this very simple understanding, you can sort of write down, basically analytically, what the typical gas mass fractions you expect if you're sort of just a core trying to accrete a little bit of an atmosphere. And what you get, so this is the atmospheric mass to the core mass ratio, or the planet mass. And you can see from this, for planets, a few times the mass of the Earth. In these typical distances, it's just like a semi-major axis, just the temperature from the star. In typical disk lifetimes of a few million years, and some very crude guess for opacities, you can just stick in whatever you think the true opacity should be in this. You find that you can accrete typically a few percent of a gas mass. Although this is very crude, I think it nicely shows why we typically form sub-Neptunes and not, say, sub-Saturns or gas giants. And I think the reason simply is that although we heard already, and I think we'll hear more about tomorrow, that runaway gas accretion, when you really run away, it's really fast and you can accrete a lot of material. Getting there is sort of the slow part. So many things get stuck on their way of becoming a runaway planet, because you first need to accrete, 10% or so in your mass. And accreting 10% in gas takes, several million years. And in many cases, your disk may go away before you manage to become sort of a more impressive gas giant. Okay, so then you can say, well, we're done, we formed our planet. Well, not really. So what we discovered next, and actually I would like to say this is maybe a nice way where you can show that trying to understand these things in a sort of more back of the envelope way complements nicely detailed numerical work, because we can now try to stitch together these different phases. So once we understood sort of the typical gas masses you can accrete, you can ask the question, what happens next? And what we realized is, as the gas dissipates, a lot of the gas you had just accreted actually is taken away. And so we call this the spontaneous mass loss phase. And so basically what happens is quite simple, actually. If you remove the pressure support, right, you imagine your planet, you move the pressure support on the outside of the disk, and so what will happen is the outer layers of your atmosphere will expand basically adiabatically into vacuum. So you don't strip the entire planet, right? But you lose of the order of half of what you have just accreted. So it's not a disaster, but just remember, when you want to build your planet, make sure that you easily can accrete a factor of 2 more in your gas than you want to be left with, because this will take some of it away. And basically what happens is the energy and basically the luminosity of the inner layers of the envelope drives this mass loss, and this will only really halt once you've lost of the order of 25 to 70% of what's in your envelope. Exactly that number depends on the structure of it. As a result, though, so you not only lose half of what you have just accreted, you basically also now, whatever is left, is able to shrink rather rapidly to smaller planet radii than it would without the mass loss. And the reason for that is because the material that's lost, of course, carries away energy. So the rest of your planet can cool extra fast, if you wish, faster than it would without the mass loss. Okay, so the upshot is, on the order of the disk dispersal timescale, right, because that's the timescale on which you lose the pressure support of your disk, the planets will shed the outer layers of the envelopes, and as a result, your planet will shrink to radii that a few times the core radius. And it's a short time scale, like, say, 10 million years, like a few times the disk dispersal time scale. It's not hundreds of millions of years. But again, so you can account for all this, and again ask, what sort of atmospheric mass fractions do you get? And you get a different but similar scaling. So again, you can still have a few percent of the cores of the planet's mass, and you get similar scalings with disk lifetime, distance, and mass of your planet. Okay, so then we thought, now we're done, right? Now we form our planets, and we just let it assembly evolve, and we're all good. So it turned out, not quite. Actually, it depends now. In some cases, yes. So in the case where most of the energy available for cooling, in some ways, if most of the heat capacity of your system is in the envelope, then indeed, now you have sort of the standard thermal evolution that people had been looking into for quite a long time, sort of seeing the planet shrink and evolve in time. And this can take gigayears, and Jupiter, for example, is still sort of in this phase, right? It's still losing more energy than it's receiving from the sun and slowly shrinking. And all this happens is, in this case, is that your rate of convective boundary will shrink and contract with time, so you increase the density at the base, and you're all good. No more additional atmospheric loss, at least not from the pure planet formation evolution part. So great, so this part is good. When is this true? When is most of the energy available for cooling or the heat capacity of your system in the envelope? Turns out when the mass fraction you accreted in hydrogen helium is about 5% or more. So if you manage to accrete 5 to 10% or more, then this is truly what's going to happen to you, and you can model this in great detail. So how about the other case? So the other case, when you accreted less than roughly 5% of your total mass in hydrogen helium, what's really interesting is that now you're in this funny regime where most of the energy available for cooling is actually in your core. And because the temperatures are very high, your core and your envelope are basically very well coupled, and they have to cool together as a system. So my envelope still, just as before, radiates away energy, right? You're losing heat continuously at the rate of convective boundary, and wants to shrink and contract. However, whenever it wants to do that, you're basically resupplying enough heat from the core that you can't really shrink. Your envelope cannot deflate, and so you continue losing mass. And so in this way, you basically have enough energy, or more energy stored in the core for cooling, more thermal energy, than your atmosphere is binding energy. And so energetically, you can lose the entire envelope. You'll strip these things entirely. There's plenty of energy to do the job. And it's at least energetically a runaway process, because as you start decreasing the envelope mass, energetically, right, the rest is even less strongly bound, and it's even easier to lose. So it's sort of a runaway process. Okay, so just to summarize these two parts, so basically what I'm telling you is the final outcome of your planet depends on where most of the heat capacities of your system, if you accreted more than 5% roughly of your total mass in hydrogen helium, you get to keep this and shrink and contract. If you accreted less than those 5%, then your cooling energy is dominated by the core, and you can actually lose your entire envelope. Okay, so we expect sort of a bimodal outcome as a result of just of the planet formation part. Is there any way to prevent this from happening? So I told you there's enough energy for the mass loss, but in some cases there's not enough time. And there are two time limits, actually. One is the age of the system, right? It may just be, and I'll show you in a second, that this mass loss can take a long time. It can actually take longer than a few gigayears. So some planets will be stuck in this intermediate regime where they're actually still losing atmospheres at this moment, driven by the cooling luminosity of the core. And the other one, even more important, and a time limit, is the following. The other way you can cut off the mass loss is that although you have enough energy to do the job, once you can cool faster than you lose mass, you can cut off any additional mass loss. And let me try to explain that. So the competition is the following. So I know my mass loss time scale, right, is simply the mass of the atmosphere divided by the escape rate, and that's given by the escape rate of the gas molecules at the Bondi radius. So it's 4 pi, the Bondi radius squared, times the density there, times the speed of sound. So the density at the Bondi radius, we know what this is because we know how it's connected to the density at the radiative convective boundary. And that actually, because this is the radiative region, so you have a profile that's close to isothermal, has an exponential decay in it. The cooling time scale, on the other hand, is just right, the energy you have available for cooling divided by the luminosity at the radiative convective boundary. There's like a bottleneck in getting rid of the heat. And you can just write down what it is. And it's the competition of the two. When you can cool faster than you lose your envelope, you cut off any additional mass loss, because once you can cool faster than you lose, cooling will lead to shrinking of your envelope, and if you can even just shrink it so slightly, you can cut off any additional mass loss because of the exponential dependence on the mass loss time scale. And we'll come back to this point in a second. Okay, this is all the. Okay, so now these are all the ingredients. I told you from sort of start to finish what do you roughly expect for this population of planets, and so you can model all of this stuff consistently. And the only thing the main thing there are very few things we truly don't know. We have to make some educated guesses about the disk lifetime and the opacities, but I will argue as long as we make some reasonable choices and stick with them and don't fiddle around for every single system, I think it's sort of a good first order approach. We know what the equilibrium temperatures are, because we know where the planets are today. And we have at least a reasonable good constraint observationally of what the core masses are in their distribution. So you can take this and then calculate what the atmospheric mass fraction is that you accrete, and then you can evolve it under the core-powered mass loss mechanism, so following whether you get to keep the envelope or lose it. And then you can ask what the outcome is. And that's exactly what Sivan did here when he made this plot. The red things are the results from his model, which shows the planet size as a function in Earth radii, and basically the relative abundance that he finds in his work. And so what you can see is that you actually get about, as expected, you get a bimodal distribution of planet sizes. These are the planets that are the stripped cores. These are the ones that got to keep the hydrogen-helium envelopes, just from a planet formation point of view. So usually this is actually explained being due to photoevaporation from the host star. So I think what's intriguing is that planet formation by itself will also give you actually this bimodal distribution. So this was sort of the status in 2017, 2018, but we can of course do better. There are much better observations. Now actually I should show you the gray lines. The gray histogram is the observations. So it was given the simplicity of the model, I think it's a very good match to the observations. But we are fortunate enough that we have actually much better and detailed observations now. And so my grad student right now at UCLA has been continuing this work and extending it. And what he's done is he's actually modeled the exoplanet population given the stellar host stars, and to look also how this will look if you make a plot in orbital period versus planet size. And this is basically what he finds. And so basically these two islands, right, correspond to these the sub-Neptunes that have hydrogen-helium envelopes. These are the strip cores. And I think you can see that it gives you very good agreement with the observations. What is very nice is, so you can explain this valley that you see in the exoplanet population by planet formation itself. So you do not actually have to appeal to the X-ray or EUV radiation from the host star. The very nice thing is, because we can actually analytically understand what is the slope here and where is it located. And the reason for that is this competition between the loss timescale and the cooling timescale. So and it depends actually on many things, right? Many quantities that we have to write down. But the very cute thing is, because the loss timescale has this exponential in it, to first order, it's all driven by what's in the exponent. You can imagine that when I change things in here a little bit, it changes everything a lot. Whereas when I change the things that are the constants in front of it, or the quantities in front of it, I can change them a lot without having a big effect. So to first order, to zero order, I can derive basically what I expect for the slope to be by just evaluating the dependencies on these quantities that enter the exponent. So what's in the exponent? It's basically just the ratio of the Bondi radius to the radius convective boundary, which is basically your planet's radius. So we can do that, or all of you can do that. It's very straightforward. The only thing you really have to do is, you know what the speed of sound is from your star. You know how that goes with period. The only thing you need to assume is a mass-radius relationship for the core of your planet, but we even know that sort of fairly well. And then you can derive how the radius of your planet will scale with period and the density you assume for the bulk of your planet. So from this, you can see that this should go as in log space as -1/9. So in which comes out to be roughly -0.11. And this is exactly also the slope we find numerically. The very cute thing is, it actually beautifully agrees with observations who basically we absolutely find exactly this value. And because of this dependence, there's also not much wiggle room. There's not many things you can play around with. Although many things go into how much gas you accrete, so on and so forth, where this value is not very sensitive to any of these assumptions. In addition, you actually know something about what the cores must be made of for the cases where you do not have mass and radius measurements, because the density, the bulk density of the core end is here. And this actually tells you that these cores must be have bulk densities of terrestrial values, basically 5.5 grams per centimeter cubed. So this is interesting, because what this tells you is, so we don't truly know how you get to those 5.5, right? How you mix your iron versus water versus silicate. But what it tells you is that they're not super water rich. In fact, we did this test. We find that at most we can stick in 20% of water and still get sort of a reasonable agreement with observations. So I think what this tells you is that these cores did not form in a water-rich environment. So it doesn't mean they have to form exactly where you see them, but significant formation significantly past the ice line is probably not the best explanation for these. And you can show that core compression is important. But let's move on, because I would like to cover a little bit more ground. The next thing that actually Akash did is, we can model in detail the host star population, because we want to see what the predictions are of this core-powered mass loss mechanism with stellar type and stellar properties, because that's one way we can actually test this and maybe also differentiate any signatures that you see because of photoevaporation in the exoplanet population and because of the core-powered mass loss mechanism. So first of all, so he modeled actually, so we know the population of these host stars. It's been fairly well characterized. And basically so this figure was made just assuming all stars are exactly like our sun. Of course, that's not true. then using the actual distribution of the stars, you get a very similar but slightly different result. And if anything, I think it matches the observations that is based on these stars even better. So this is just a sanity check. Okay, good. So modeling more realistic cases gives you better agreement with observations. But what we really were interested in is looking at, for example, what we predict as a dependence of, for example, stellar mass or luminosity. So I'm giving you one example. If you want to know more about metallicity and age and other things, I'd be happy to show them to you later. So here's the example of what we predict the dependence of this value is. So that's dividing those two exoplanet populations on stellar mass. So in the core-powered mass loss mechanism, the thing that matters is the stellar bolometric luminosity. So you may wonder, why does it matter at all? It matters because it sets the outer boundary condition in your mass loss, because you have energy that's escaping from the interior of the planet that's driving the mass loss, but you need the star to maintain the isothermal profile that's connecting basically your radiative convective boundary to the Bondi radius where this mass loss is happening. So this is where it matters. And so somebody suggested to me we should call this bolometric luminosity-driven photoevaporation, but I don't know if that's sort of the right terminology. Okay, so so the bolometric luminosity matters because it sets this outer boundary condition, and you can see how it matters because again it sort of sets this. It enters through the speed of sound here, and now it's the same equation, right? No, I'm just plotting it in a different parameter space. I'm plotting it in the space of sound speed, which you can translate to sort of the equilibrium temperature of your planet. And here, then the planet radius as before. And what you expect, or what you get, is that you get a slope of 0.3. So you expect that more as you go to higher mass stars, that the valley that's separating the sub-Neptunes and the super-Earth will go to larger sizes because you have higher bolometric luminosities, and therefore you can drive more loss. Basically, a larger planet, a higher mass planet, can be stripped if you have a larger bolometric luminosity. This is where this dependence comes from. And so you can do this analytically. You can, of course, also do that numerically. And again, I think the slopes agree very well. So this is the numerical result. This is the analytic derivation. And intriguingly, this is actually what's been reported when people looked at the observations. So this is from the same Fulton and Pitagora paper, where they plot planet size as a function of stellar mass, and they do find this trend in the observations, and also the magnitude is almost identical. Similarly, this was also shown by Yanxin Wu. In her case, she actually used this and then interpreted this entirely in the context of photoevaporation. And if you do that, you get a very different result. So if you try to, first of all, if it's photoevaporation, you would not expect this positive trend of this valley with stellar mass. Why is that? Because in photoevaporation, right, lower mass stars are the ones that have higher X-ray and EUV luminosities compared to the bolometric luminosity. So if you can keep, now it depends a little bit whether you keep your effective temperature space constant or your period distribution, but to first order you expect a flat slope in this space. At best, a very weak, either positive or negative dependence, depending exactly on how you choose your sample. So then when Yanxin Wu tried to explain this observation, using photoevaporation models, she reached the conclusion that you have to change the underlying planet mass distribution to get this positive slope. So she concluded actually in her paper that more massive planetary cores have to form around more massive stars, and then you can match this trend. So under the core-powered mass loss mechanism, we don't find any evidence for this. For us, with the same underlying planet mass distribution, we get this trend because it's driven by the stellar bolometric luminosity. So this is one way, one example, where the core-powered mass loss mechanism gives you a very different prediction from photoevaporation models, and you can observationally test this. I know it's not easy to get masses of exoplanets, but you know, the observers are working very hard, and our sample, I think, will be large enough to just clearly test this. Okay. So let me briefly summarize this part, because I would like to tell you a little bit about something else too, but I'd be happy to, if you want to know more about this and other dependencies on stellar properties, I have plenty of more slides. So, but let's summarize this part, okay? So what I tried to show you is that basically core cooling, so the energy that you have left over, if you wish, from planet formation itself, alone can produce the radius valley in the exoplanet distribution. What we find is actually light atmospheres energetically can be lost entirely, whereas heavy atmospheres can cool and contract over gigayear timescales. So the conclusion of this is actually that the majority of observed rocky planets that we currently see in the exoplanet population are consistent with being stripped cores rather than having formed as a separate rocket terrestrial population. And they look somewhat water poor, so I think most of them did form probably inside the ice line. Other interesting things you can test observationally, the core part mass loss mechanism, it continues, right? It happens on gigayear timescales, even today. So as you wait, or if you're able to probe planets, super-Earth and sub-Neptune populations around different age stars, you should see that the population of super-Earths keeps increasing as you go to older and older stars, right? Because even between 500 million years and 5 billion years, you're still turning sub-Neptunes into super-Earths by stripping their envelopes, which is also different from photoevaporation because that happens basically within the first 100 million years. Core cooling, I showed you, depends on the volumetric luminosity of the star, and that's why you would expect the radius valley to shift to larger planet radii for larger stellar masses without changing anything else about what's going on. So no changes to the underlying mass distribution. Ultimately, I think we really need to combine photoevaporation and core part mass loss models to correctly interpret the observations when we reach conclusions about the bulk densities, for example, about the cores. We sort of find very similar results, but both of those should add together at some level. So this is something that I'm currently working on with James Owen to correctly combine those two so we have the correct mass loss models. And as a transition to my last points, I think there is evidence that there is more compositional diversity in the exoplanet population than only predicted by gas accretion and loss alone. To first order, if you look at the overall statistical sample, it works beautifully. But I think they're starting to emerge, or at least it looks to me that there are a few examples where there may be something else going on, or something in addition, I should say. Okay, very quickly, I would like to tell you a little bit about collisions. So there are many ways in which I could motivate why it's interesting to look at collisions and what happens to the atmospheres and giant impacts, because we know that the terrestrial planets assembled with a phase of giant impacts. We've seen more and more evidence that they may play an interesting role in explaining some of the tightly packed planetary systems. But whatever your reasons, I'll tell you a little bit what I think about those collisions. So one application would be this, right? We see that Kepler has many of these tightly packed systems. But what's intriguing is we know they should have formed in a gas disk because we see hydrogen-helium envelopes. But the intriguing thing is that many of them are not in these mean motion resonances. And there are many ideas why this is not the case. One of them is that as the gas disk goes away, that these resonant chains that used to be stable because you had a nicely tightly packed system become unstable. And a fraction of these systems seem to be consistent with that, in which case you get giant impacts, which then again give you sort of long-term stability for your system. So this led me to wonder, what would those impacts do to the hydrogen-helium envelope that you had with you? And so when you think about giant impacts, it's actually a sort of really beautiful physics problem. And it's also a beautiful problem because it shows the need to combine the analytic and the numerical work. There are two parts to them that are important, actually, especially if you care about hydrogen-helium envelopes. The one is the mechanical part of the impact. So you have an impactor hitting a target, a strong shock is launched, it propagates to the entire target, and then that shock basically launches another shock at the planet surface atmosphere interface, and then that can drive the mass loss as the shock is accelerated in the atmosphere. And then there's also a thermal part, because that same impact, some of that kinetic energy is converted into heat, and that will basically heat the core of your planet. That core will again start to heat your envelope, and it can drive mass loss, like thermally. So just briefly looking at the mechanical part, this part, actually the atmospheric part, how the shock propagates in the atmosphere and fraction is lost, is best done analytically. You can do it numerically also nowadays, but basically you get self-similar solutions. You can write it all analytically, and it's sort of cute, and you can understand, right? Of course, there are two parts to your mass loss, overall mass loss. There are parts on the planet where your shock on the surface is fast enough, you lose everything on this point, but there will be parts on your planet where the shock itself may not have high enough velocities yet to lose the bottom layer, but because your density decreases as you go up in height, you accelerate, the shock accelerates, and you can lose sort of the upper layers. But the upshot is you can lose a significant fraction of your atmosphere, but it depends on what the ground velocity is that launches a shock into your planet. And this is sort of depends on how your shock propagates to the solid part of your planet. And this is a nice example where especially new moving mesh hydrodynamic simulations have been valuable, looking at the shock propagation in a more precise way and calculating what are the resulting ground velocities. So you can put these two together, and what you get is, in a typical impact that comes roughly at the escape velocity and is comparable to u in mass, you typically get sort of half of your entire envelope stripped. And in addition, especially if you have hydrogen helium envelopes though, you also have heating. And what this heating will do is it will heat your core, and then this core will transfer some of that heat to the atmosphere. And it turns out that this can be way more efficient in unbinding your atmosphere than the shock component itself. And the reason for that is actually pretty easy to understand. So the mass of the impactor you would need to lose your envelope, that is basically the ratio of the mean molecular weight of your atmosphere to the core. So basically the reasoning is because if you have hydrogen helium, you only have to heat your core a little bit, or only to a few thousand or 10,000 Kelvin, to unbind that atmosphere, which corresponds to an impactor mass that is lower than the core mass by this ratio of the mean molecular weights. Or thinking about it another way, if you want to have a shock that has velocities comparable to the escape velocity when it emerges on the other side of the planet, that corresponds to temperatures that would be enough to basically give escape velocities to all the particles in your core. But you would then be enough energy to disperse the whole planet. You don't want to do that. You don't need to do that. You only need to get rid of the atmosphere. And so because of the lighter molecules, that corresponds to an energy that is lower by essentially this ratio of the mean molecular weights. Just thinking of it as an ideal gas, but it gives you the sort of right understanding. Then you can do this super fancily. You can do these impacts. You can follow the expansion of the atmosphere. You can calculate the mass loss, and that's what John Bierstecker did here. And basically, you can do this for different atmospheric mass fractions, but you can see that the mass ratio of the impactor to the planet's mass to get complete atmospheric mass is less than a tenth. You know, it could be even a 20th or a 50th, depending on whether you have 2% or 10% in your envelope, especially if you're close in. So the upshot is actually, and this is the shock component, which is all the way down here for those. So actually, for hydrogen helium envelopes, the thermal heating part can be more important, significantly more important than the shock component when you worry about atmospheric loss in giant impacts. And a single collision, therefore, should easily be able to strip your entire envelope if you have hydrogen helium in it. Okay, so this is my second part of my conclusions. So atmospheric loss due to the thermal component typically exceeds the shock component by really a significant fraction. So you often only need sort of a tenth of the mass of the target to really lose hydrogen helium envelopes. So you can easily strip those envelopes in giant impacts, like maybe too easy. Um, so this is something to keep in mind. I think it's a very intriguing idea. So I think what this tells us, if you really had these collisions late in the system, we should see observational imprints in terms of when we look at the bulk composition of these planets. Um, and I think it may be an interesting explanation for some of the diverse bulk densities we see in some of these multiple planet systems, especially if food evaporation or core cooling doesn't give a nice self-consistent explanations of these systems, then these could be imprints of these late collisions. And with that, let me stop here, and I'd be happy to take any questions. Yes, Daniel. Oh, sorry. I'm like.
One more complexity on top of everything you said is you can store gases in the hot mantle where planets where it is very hot, have your collision, strip atmosphere, and later have planet cool and outgas some of that.
Excellent. Yes, absolutely true. Typically, you would then outgas a higher mean molecular weight atmosphere, which is also interesting because that could give you like a secondary atmosphere. So
Well, like pure hydrogen dissolves in magma, and
right,
you
but
can store a percent of.
yes, so a
the mass.
percent, I agree, but probably not more. But I think it's even more intriguing if you think about secondary atmospheres and sort of habitability and stuff, because you actually may want to have some of that happen. So yeah, I agree.
To use the radius distribution, these two peaks and the valley, to constrain whether giant impacts actually happen in most Kepler planets and the properties of giant impacts, the size of the impactors, and so on and so forth.
Yeah. So so of the valley, I think no, because the broad properties I think are very well explained by other mechanisms. So, but I think if you look at a given planetary system where you would have very precise expectations what the atmosphere to core mass ratio should be, that I think you can use. If you have deviations from that, I think these impacts are sort of an attractive explanation that would explain that, and then you can use that. So if you're willing to do all those logical steps, you can use that to constrain properties about the impact.
Yeah, what it means is if you can constrain whether giant impacts happen.
So
assume
yes.
your model of like
So we know,
core mass
right?
loss is happening,
Okay,
and
so
it's shaping or photo evaporation, and whether giant impacts put planets in the valley. You can say, no, it's actually not fitting the data, so maybe
yes.
giant impacts are not happening.
Yeah, so I
generally.
think what you can say is this. So as I said, so I hope you all took this away, that to zero order, I think it's the formation signature. It's this core part mass loss, and then and probably with some combinations of photo evaporation. However, for example, if you would find a stripped core, I don't know if I can easily go back. Let me go. Right, and so I think you can say we can know that it's not giant impacts giving rise to just this. So I don't think this is a signature. However, if you find a stripped core in this population where both photo evaporation and the core cooling will tell you that you shouldn't be able to strip this core, then you can have two options. You can say, oh, this must have been a giant impact. Absolutely, because neither of the other ones work. Or you could say, I formed a true large terrestrial planet, like a true super Earth formed but after the gas has gone and it formed that way. I think these are your two options.
Another option is, sorry, can I comment on that? There are known systems where the other, where you have two planets, where the outer one is has no atmosphere or little atmosphere, and the other one does. It would be hard to explain that.
Yeah, this is
through
what I
anything
alluded to,
other
right?
than-
This is where the planets listed on the bottom here. So when you have multiple planet systems.
Right, like Kepler 36.
Yeah.
Kind of, yeah.
You mentioned briefly that there are some exceptional systems, and they may be errors, of course, but for example, Kepler 51, if I have the number right, this is a planet where it supposedly has a mass from transit time of about 2 Earth masses, but an atmospheric radius of 2 Earth masses, an atmospheric radius of 7. And so you would expect very rapid atmospheric loss from just Parker wind or something. Do you have a wrinkle that can save those things?
Um, I I'm not sure this is the same planet that I checked earlier, but I don't think just from that observation alone you can conclude. Well, it depends on where it is with respect to the star. So we need to check that. We can check it
500 and
afterwards.
something is the equilibrium temperature.
Like-
There's a paper by Cobillos et al. In 2017, which complains about a whole list of such objects which seem to have anomalously large atmospheres for their mass.
So, but as I told you, so the core powered mass loss is like a Parker wind, right? The way you drive the mass loss, and it would give you a larger planet radii because you're still in this mass loss phase because you're basically not cooling and contracting.
Right.
And
Problem
we
is
looked.
the
I don't
system
know.
is so unless the system is extremely young. I mean, the time scale for that system, I think, is thousands of years or something to lose the mass.
So we should check this because so this is right. The core powered mass loss thing would continue over gigayear timescales. It depends exactly where it is. So if it's super close, it can be fast. But because you need to lose the material at the Bondi radius, this timescale can be long, and it's regulated. The heat is sort of resupplied by the core, and so I'm not sure that this number
Well,
of
one way to
1,000
put it
years
is
would
that
be
the
correct.
argument of the exponential in your form is about, depending on whether you use molecular hydrogen or atomic. For molecular, it's about 8. It's not a very big number. Another way of saying material.
But it depends on your energy budget, right? So we should look at that. If they didn't account for the energy budget in the core, you would get a much shorter time scale. We can just look at it and check afterwards.